Good morning, everyone. My name is Nate Newby. I work in the exercise lab here at NASA, the Johnson Space Center. I'm going to talk to you a little bit today about some wearable technologies that we've been testing in our lab, one of which we help build in the lab. Other two are purchased or collaboration builds for us. Up front, I'd like to thank my colleagues on this effort, Megan Downs, who is here today, and Andrea Hansen, who's away on travel. So just, I know not all of you are NASA folks, so just a bit of background introduction. So humans decondition in the weightless environment. And actually this is an adaptation to the weightless environment because you don't need really strong bones, 1G bones, 1G muscle strength when you don't have any body weight or gravitational force on you. So it's an adaptation to that environment, but it's not convenient when you want to land back on Earth or another planetary body where you need that strength. So we've developed a whole suite of countermeasures for ISS to try and maintain the 1G strength throughout their mission on ISS. Paramount among those is exercise, and we do a lot of it. We do about 2 hours a day of exercise up on the ISS. And so we're interested in sensors that can monitor the daily exercise performance, the quality of each bout of exercise, and also the cumulative effects of exercise and the adaptations. We think, as was mentioned in the opening comments, that this sort of technology is going to be more and more useful as we have these large communication delays with the ground, so the crew can monitor their own performance and help tailor some of their training. We think it's important also to use the ISS as a lab, as a test bench for these kind of technologies before we actually need them for the future missions. And just a few issues we've had currently on ISS with communication is it usually requires large equipment. We're not going to have that luxury in these future missions. There's a need for time-consuming setups and calibrations. And we've also seen that some of these data systems have interference in the environment or in the suit. So I'm going to talk to you about 3 technologies today, just touch on them lightly: force shoes, a biomech suit, and an earbud sensor. So force shoes, the work here came from our inability to measure the underfoot forces when we were doing resistance exercise on our primary piece of exercise hardware, the ARED. So one category of portable devices we've been looking at is force plates that you essentially wear on your feet, or force shoes. So with ISS and the Human Research Program here at NASA, we built in-house these what we call X2 force shoes. And they're essentially an Adidas weightlifting shoe that we hauled out the sole and embedded, oops, let me go back here. And we've embedded 2 force plates, essentially one in the toe, one in the heel. They have 6 degrees of freedom load cells in each one, so we can measure all the moments, all the forces. They also have inertial measurement units in each one, so we can measure the accelerations and the angular rotations. We've done a lot of testing, extensive testing of these shoes, and they perform quite well to laboratory-grade force plates. In the middle of the shoe, it's powered by a lithium-ion battery, and behind that is essentially the guts of your cell phone. So it can do the A to D conversion of these. It can do filtering. It can store data locally, or it can Bluetooth it to a laptop. So why would we be interested in measuring underfoot forces? Well, if we combine that with kinematic measurements, we can then get a sense of the joint torques that people are experiencing when they exercise. We can also, as seen in the little video there, we can put it into a model and get an estimate of the muscle forces and activations going on during exercise. And why is that important? Well, exercise in weightlessness is very different from exercise on the ground. So you don't have this distributed load of your body. You only have the load that's applied through the bar or harness through the exercise device. And so that is a unique kind of loading on the body that we only see in microgravity. And also, we have to vibration isolate these devices so that they don't put loads into the wall of station. And so that leads to some unique motions that we don't see on the ground. And final point here is that we see a lot of variability in the strength of crew members coming back. Some do very well, some do not as well. And we think part of it might be due to the quality of the exercise differences amongst crew members. So we like to be able to measure this more accurately. Why use shoes? Well, a traditional set of laboratory standard force plates are on the order of 30 to 40 kilograms. Of course, this is way too heavy for our future missions, and to put it in perspective, for the Orion vehicle, the new vehicle we're developing and that's the part the crew will land back in Earth on. We're allowed only up to 10 kilograms for the whole exercise device, bars, harnesses, everything. So we blow the budget with force plates. The shoes now we have down to a little under 1 kilogram for each shoe, which is a nice weight for maybe just resistance exercise, but if we wanted to use them for running, I think we would like to get that weight down a little lower. So that's an unmet need for this technology. Motion capture suits is another technology. Now we've purchased the suit on the left here, the MVN Biomech suit. It's a full body human motion measurement system. It uses inertial sensors that you place on various segments of the body. We think it could potentially be used on ISS and potentially also used inside the EVA spacesuit, because there's a movement inside that suit. It's not fit like a glove, and it's hard to measure that sort of movement. Why are we interested in this technology? Well, it's very difficult to do traditional video-based motion capture on orbit, and you can see our crew member here trying to do a bench press and essentially has to put their feet straight up and down so they don't interact with the wall and the stowage at station. And so it's really hard to get the full panoply of cameras that we would need to do 3D video motion capture, and we can't get the cameras back far enough oftentimes, so we have to put these distorting wide-angle lenses that are sometimes really tough to calibrate out. So the suit would offer an advantage in that it's lightweight, it could be used in these confined spaces, and that generally they're very easy to use and set up. You put on, you take a pose, you hit a button, and you've calibrated the whole system. The unmet challenges with this is most of the suits we've seen rely on gravity to orient the position of the IMUs and map them to the body, which of course we won't have up there, so we would have to come up with some way around that. Most of them also use magnetometers to help in the calibration, but also to help eliminate drift. And on ISS, we are within the magnetosphere, but I'm not sure how well it would always point to true north up there. And once we get out of low Earth orbit, then that's no longer an option for us. The last technology I want to talk to you about is the earbud biosensor. And this is a partnership we have with Cooper Consulting. And they developed a sensor that measures heart rate, core temperature, and blood oxygenation levels. So why are we interested in this? Well, we could use this to improve and monitor capabilities during both exercise on ISS and also in the suit, which was very important. We have very little information about human physiology inside the spacesuit. So our development efforts to date here is that we've tested this system on a treadmill during exercise and also in the spacesuit. And the results of those tests led to some improved filters, some shielding that we needed to do, and then some updated firmware. Cooper has since, so this is what we started with, this suite of sensors here. Cooper has now made that into this small earbud-worn sensor that you see here, a very nice form factor. We're pursuing collaborations with other partners and looking to maybe use this in analog space environments. Some of the challenges here is we would really like to have a real-time sort of display and sort of a risk assessment algorithm, like a red, green, yellow or something, especially in the suit, using the heart rate, core temperature, and blood oxygenation to give the crew member a clue of how well he's doing and whether or not he needs to be taking some action. We also had some issues with the data quality inside the suit and getting that out of the suit, so we'd like to see some improvements there. And we'd like to add some two-way voice comm to this system as well. And finally, we're very impressed with the sensors that we've tested so far. We think before they can be used as standalone units, they need some improvement. The shoes need to be lightened up a bit if we're going to use them for running. The motion capture suit is lightweight, can be used in small spaces, but there may be some issues with accuracy when we get in microgravity, and the earbud sensors provide some nice additional tools, but the data quality needs to be somewhat improved. I do have all three pieces of these technologies, these hardware here. They're in the back of the room at a table, so maybe at the break or something, if anyone wants to take a look at them, I'd be happy to show you those. And thank you.